Welcome to lectures on policy gradient methods in artificial neural networks. In this video, I will show why it's important that you subtract the mean of the reward via the value function and how you can do this. Let's go back for a moment and look at the one-step, one-horizon policy gradient methods. We found that we have an update rule that has the reward and some terms that come from the derivative of the logarithm of the policy. And then we said if this is a solution, then this is also a solution. What's the difference? In this second case, we would subtract a baseline. And then both algorithms will have the same solution. In expectation, they will find the same set of parameters. Now, in the lecture on multi-step policy gradient, we found that algorithms have many terms, not just one, but all of these terms of the form that you have a return from the momentary state to the end, and then you have the logarithm of the policy. And this is one term with AT-ST, then there would be a second term with AT plus 1, ST plus 1, and a third term, and so forth. And then we can make the same argument as before. We can say, well, if this is a solution, then this is also a solution. The only difference is that we subtract a baseline. And now, I said there are many terms in of that form, and these terms would be different. One is for ST, one is for ST plus 1, for ST plus 2. Well, the baseline that we subtract may depend on the state. So we arrive at a reformulation where we have several terms of this policy gradient and this is one term, this is the term with ST, and we subtract a bias, and a good bias should be something that's very close to the mean, to the expectation value. And that means as a bias, we should take the value function v of s, the value function that we know from TD learning. So here's the basic idea. If you want to implement this with deep reinforcement learning, and this is just a glimpse, we'll do this more rigorously in a separate lecture, then you would have two networks. One network has actions at the output, the other network has the value at the output, and you feed the value into the main network so that you can subtract a reward baseline. The value is the reward baseline, and the value itself is also learned. So more formally, we can say I have a network on the right-hand side which provides the baseline, and this network is estimating the value function v of x, and the input are the states, and we start in state as t, then we go to st plus 1, st plus 2. Each of these inputs is one of the inputs, and it's given to both networks, the value network and the second network, and the second network has outputs that are the policy, the probability that you take a certain action. And this network has parameters theta, and the other network has parameters w. And if you do this now in this formal algorithmic fashion, you have the same kind of idea as before. The only difference is that we now always subtract from the return the estimated value, where the estimated value comes from the second network. So why is it important to subtract a baseline? And why is a good baseline the expectation value or the mean? Well, the statement is that subtracting the expectation normally provides estimates that have smaller variance. And let me show this with a little example. Suppose we have samples k, and we want to have something like xk minus x bar, yk minus y bar, where x bar is the mean over all the x and y bar is the mean over all the y. And I want to calculate the mean of all this. Okay? Now, one sample in that case is, well, it's just xk minus x bar times yk minus y bar. Now, let's do this something very similar, but now we consider the following. We consider xk times yk minus y bar. And again, we look at the mean. Well, by construction, because y has a mean y bar, and I assume that the two are not correlated, x and y are independent, then this is 0. And of course, this is also 0 on the left-hand side. So the two situations have the same mean. But now let's look at this one specific sample, and I write it as xk yk minus y bar. I rewrite it as xk minus x bar, yk minus y bar, xk minus x bar, and then we have x bar yk minus y bar. So this is just a rewrite. The advantage of this now is that I have here one term that's exactly the same as on the left-hand side. Now let's make an example that we get a feeling of the variance. Suppose that the x's have a mean of 5 plus minus 1. Suppose that the y have a mean of 8 plus minus 1. So two independent variables, one has a mean 5 and standard deviation 1, the other one has a mean 8, standard deviation 1. Then if we evaluate this term here, we have basically a multiplication of two terms that are both of order 1. Yeah? So now let's turn to the right-hand side. So this would also be of order 1 because it's the same term as on the left-hand side. But then I have another term, and x bar is in fact 5. And then this is again order 1. So each individual sample now has sometimes a 5 with a plus sign. Next time another sample will have a 5 with a minus sign. So overall I've added a random variable which is in the range of plus 5, minus 5, plus 4, minus 4, so maybe even sometimes plus 7, minus 7. They will all average out to 0. But each individual sample is now has much larger amplitude. So this just adds noise for the total evaluation. When we go back over many samples, we would average. In both cases, if we average a lot, we could zero on the left-hand side. We stay always much closer to 0 with our estimations than on the right-hand side with the blue example. So subtracting the mean x bar is important. And now in your mind, just replace x bar by the value and R and X by the reward, the momentary reward. So R minus R bar is an estimator that's much more efficient than just working with the reward itself. So yes, subtracting the mean gives smaller variance. This is for the simple example, if you really have a multi-step horizon policy gradient, the arguments would be more complicated, but the general idea is qualitatively the same. So let's have this quick outlook into deep reinforcement learning. In deep reinforcement learning, you often have a structure where you have an actor part that has an output that is the policy, the probability of choosing a certain action. Then you have a critic part, the output is the value. This one has to be the left-hand side has to be optimized with the derivative of the log policy, and the right-hand side is optimized either by actual return minus V or using some tricks from TD learning. And in the end, this difference is the actual return minus some mean, and that's used for updating the parameters of both networks. And here's an example that has basically this structure with two differences. The first difference is it's not a completely separate network, but the values just take the solution given by a hidden representation of the actor network. And the second difference is that you don't work with returns and Monte Carlo sampling, but you learn the value function with tricks from TD learning. So this was a big series of lectures on policy gradient methods. The basic idea is, yes, we learn actions. We don't worry too much about Q values. We go directly for gradient ascent of the total expected discounted reward. Now, in order to go from batch to online, we use the log likelihood trick, and this is necessary because if we run online, we need to get the correct statistical weight. The policy gradient algorithms always lead to parameters update that contain the return and the derivatives of the log policy. Well, we want to subtract the mean reward, and the reason is that this reduces the noise of online methods. And if we subtract the mean as a baseline, which means we take the value as a baseline, then in fact we arrive at actor-critic architectures that are used in deep networks and that are very powerful. And so suddenly the value function and the ideas of TD learning come in through the back door into policy gradient algorithms.